Good evening everyone, I am Mr. Rich. Thank you for joining me for this interesting video over here. If you took an interest in precalculus, you will have come to realize that the topics of precalculus will directly prepare you for what you see here before you. Limits, graphs, and asymptotes. And these three items over here are directly involved when you're looking at the initial topics of calculus. So having a good foundation in this prepares you for everything that follows. Having a good foundation pre-calculus prepares you for what you see over here. We are looking at a few questions in this video. Limit as x approaches 3, we have x squared minus 9 or x squared plus 2x minus 3. When you're looking at this, you're thinking about a rational function, and when you're thinking about a rational function, you're always thinking about asymptotes. But before you do the asymptote calculation, you're always thinking about simplifying your rational function so the calculations afterwards become easy. So the first step when you see here is always to simplify. You have x squared minus 9, which is x minus 3, it's x plus 3. In the denominator, you have to factor this out. You have x plus 3 and you have x minus 1. When you look at this, these cancel out. So essentially your entire limit function becomes x minus 3 over x minus 1. Now it is from here you want to do your asymptote determinations. You know you're thinking about vertical asymptotes, horizontal asymptotes, and oblique asymptotes, but there's no oblique asymptote which you will see over here. It'll just be a vertical and horizontal, and you know I've presented videos on asymptotes. You're looking at n and m values. N is the highest order of the numerator polynomial expression in terms of exponents, the highest degree of order of exponents in the numerator, the highest degree of exponents, order of the exponents of the denominator polynomial expression. Here in the numerator we have the highest order of 1, in the denominator we have 1 as well. When n is equal to m, you're going to have a specific type of horizontal asymptote which has to be calculated. And also here you have a good vertical asymptote. Anything which will zero out your denominator will be your vertical asymptote. If x were equal to 1, you would zero out your denominator, and this right here would be a vertical asymptote. The horizontal asymptote can be easily calculated. You do x minus 3 in the numerator divided by x. In the denominator you do x minus 1 divided by x. You simplify that. When you simplify that, you get 1 minus 3 over x divided by 1 minus 1 over x. As x values approach infinity, these zero out. You get 1 over 1, which is equal to 1. So your horizontal asymptote y is equal to 1 is determined. There is no oblique asymptote. So now you have everything you need to know for the graph of this function. So now with this information here, we can easily do a graph. You know we have a vertical asymptote at x equals 1. We have a horizontal asymptote at y equals 1. Our graph would look something like this, going across these asymptotes. But you see what you have over here. We have to actually answer this question. Limit as x approaches 3. We're plugging everything into this right here. You can use a direct substitution property because 3 very well falls within the domain. Here this is x approaching a. This a value of 3 very well falls within this. According to the direct substitution property, you can actually plug this value right in here. You do 3 minus 3 over 3 minus 1. You get a 0 over a positive 2, and your answer would be 0. So as values approach 3 from the right and from the left, your function right here will approach this specific value, and this value would be equal to 0. And that interestingly happens to be an x-intercept. This x-intercept right here would be 3 comma 0. And that right here would very well be an answer to your limit. As x approaches 3, your function approaches 0. This next question is exactly the same function, but here the limit value has changed. Limit as x approaches minus 3. You know all of this rational function simplifies into this, and you know we've done the asymptote calculation over there. We have x equals 1 vertical asymptote and y equals 1 horizontal asymptote, and the function is graphed for you. As x approaches minus 3, we're looking here at a value here minus 3. You're either looking at it from the left and you're looking at it from the right. This function will approach a specific value. What is that value? Since again minus 3 falls very well within the domain of this function here, you can use a direct substitution property and just plug that value into your limit function and actually come up with an answer. You put minus 3 right here into places of x right over here. That's a direct substitution property, and I've presented a video on that. You do minus 3, and minus 3, minus 1. You get a minus 6 over minus 4, and the answer is 3 over 2. So what does that tell you? This value right here, if you were to look it across right over here, it would be a y value of a 3 over 2. Is there another way you can do the same question? Yeah, there is. You can do approximation of values. You can look at left hand values and you can look at right hand values with regards to minus 3. A good left hand value would be minus 3.001. A good right hand value to minus 3 would be minus 2.999. All you'd have to do is plug these values right here into this, and into this equation right here in places of x, and you'd get an answer very close to 1.5. We can just, for interest sake, just do minus 2.9 right here and see what happens. And I get, with this value right over here, I get a 1.500125. As we add more 9s, we'll get a value which is directly equal to 1.5. But this question has been solved. Again, for our next question, we have the same function, but the limit here has changed again. Limit as x approaches 1 from the right. We're looking at this value. Supposedly 1 is, you know this right here, x equals 1 is our asymptote. As the function approaches this vertical asymptote from the right, what happens to our function's limit? You know, you can just look at it in terms of the graph, and you know your graph dips down. This function dips down towards minus infinity, and that right there is your answer, minus infinity. But how can we do this without having to actually use a graph? Well, again, you do the rational function, and you know when you do the rational function, you get x minus 3 or x minus 1. In this instance, you take this value over here, and you know when you plug it right here, you zero out the denominator. But you're looking at everything here from the right side, so you take a value close to the right side. You can do 1.001, a right side value. You plug this 1.001 in places of x and see what happens. When you do this value over here, you get a value minus 19,999. Then it tells you, as you add more and more zeros, this value will become larger and larger in terms of a negative value, and you'd get minus infinity. But very clearly, just looking here from the curve, you can see from the graph that you're going to graze down this vertical asymptote towards the region of minus infinity, right over here in the region of minus infinity. But that's just looking at this function here, limit as x approaches 1 from the right. What if your question was limit as x approaches 1 from the left? When you're looking at this function approaching the vertical asymptote from the left, you're looking at this side, and you know your function goes or exceeds out of bounds, but it exceeds out of bounds in the direction of positive infinity. From the right towards this vertical asymptote, you're going to minus infinity. From the left towards this vertical asymptote, which has a value of 1 over here, you're going to positive infinity. However, if the question for the same function was limit as x approaches 1, see, we're not talking about 1 from the right or 1 from the left, but just 1. In this instance, your answer would be D and E. Limit does not exist. The reason why the limit does not exist here is because the left hand limit, which happens to be a positive infinity, and the right hand limit, which happens to be minus infinity, are not the same. If the right hand and the left hand limits are not the same, then the limit in general for that function does not exist. But for this specific instance, you can say one-sided limit exists. The one-sided limit is minus infinity from one side and it's positive infinity from the other side. This question here will prove to be quite interesting. We have a rational function 2 divided by the root of x minus 4. We can again try to do asymptote determination over here. We know n, the highest order degree of the polynomial exponent in the numerator, happens to be a 0, because think about it, you have a 2x to the power of 0, which is the same thing as that 2. The highest order we're seeing in the numerator of an exponent is a 0. In the denominator, we happen to have a 1, because you have x to the power of 1 minus 4, and then you have a root, so it's just a 1. There's going to be no oblique asymptote at play over here. Oblique asymptotes only come into picture when n is equal to m plus 1, but we don't have that case at all. However, vertical asymptote and horizontal asymptotes exist. What's our vertical asymptote? Anything which zeroes out your denominator will be a good vertical asymptote. If we were to put a 4 over here in place of x, you'd get a square root of a 0 in the denominator, and you cannot do that. So x equals 4 is a good vertical asymptote. Do we have a horizontal asymptote? Yes, we do. When n is less than m, you have a standard horizontal asymptote of y equals 0, which is basically your x-axis. So my x-axis over here serves as a horizontal asymptote. My vertical asymptote here is x equals 4. And now you can easily graph this. You're looking at a function which looks something like this. It's going to go vertically up against this line, and it's going to go horizontally across against your x-axis, which is your y equals 0. Limit as x approaches 4 from the right. Limit as x approaches 4 from the right. You're looking at these values approaching towards this. What happens to your function? It shoots out of bound towards the direction of positive infinity, and that ends up being your answer. But how could you actually solve this in a different way? You'd have to look at just right-hand approximation values. A good value close to 4 would be 4.0001, and you can take this value and plug it right here in place of x and see what happens. When I plug this 4.001 in place of x and I solve this out, I get a value of 200. As I start plugging in values which are having more and more zeros closer to the 4 value, this value will increase up to positive infinity. That is, your function will shoot again out of bounds but in the direction of positive infinity, and this right here would be your answer, positive infinity. Again, this right here is a one-sided limit because there's no limit which can be calculated from the left side because there's no function aspect on the left side. Even if this was a discontinuous function, which it isn't, there's nothing here on the left side, so this is a pure one-sided limit and its value is a positive infinity. So we'll end our video with this last interesting question. We have limit as x approaches 1, we have that entire function before you, which is a rational function. When you're thinking about rational functions or you're dealing with them, simplify them. Common denominator, you have 1 over x minus 1 plus, what's the factor of that? You're going to have an x minus 1 and x minus 2. You can get a common denominator here, which is just x minus 1 and x minus 2. This goes in this x minus 2 times plus 1. You end up getting x minus 1 or x minus 1 times x minus 2. These cancel out. Everything simplifies to 1 over x minus 2. From this now, it's very easy to determine your asymptotes and make a graph. Highest order of the numerator exponent is a 0. Highest order of the denominator exponent of this polynomial is a 1. When n is less than m, you still will not have an oblique asymptote, but you'll have a horizontal asymptote. The horizontal asymptote will be your standard y equals 0, your x-axis. Your vertical asymptote will be what will 0 at your denominator, which is x equals 2. So we got good information right here to make a graph. My y-axis is my horizontal asymptote. My x equals 2 is a vertical asymptote. And we can easily graph this. Our graph will be something like this. Right over here. But what's the question asking? Limit as x approaches 1. We know this right here is x equals 2, so x approaches 1 will be somewhere right over here. As x approaches 1 either from the right or x approaches 1 either from the left, you gotta look down on your curve and then look across. What is this value right here? This y value. Well, it's hard to say what it is just by looking at the curve, and you know the graph is not drawn to scale, it's drawn with the hand. Since this value right here, 1, x equals a or x equals 1, 1 happens to be very well within the domain of this function, you can easily use a direct substitution property of limits and plug this 1 right into this right over here. You'll get 1 over 1 minus 2, which is 1 over minus 1, and your answer will be minus 1. So this y value here will be minus 1. So what's the answer going to be? It's a minus 1 using the direct substitution property of limits, and I refer you to that video of mine because it'll talk more about when and under what conditions you can use this direct substitution property of limits, which is very useful to know because in many instances for rational functions and for polynomial expressions, that direct substitution property of limits comes very well into play. Again, in this video we're emphasizing the use of graphs, the use of asymptotes, and then the use of your basic limit solving skills, most commonly the direct substitution property. And that's it for this video. Thank you for watching. Have a nice day.